Hello, this is Shamul Haq here. I am here to explain comprehensive network side channel mitigation in the cloud. Side channels in the cloud and our system Pacer, which is designed to mitigate network side channel leaks for infrastructure as a service cloud tenant. So let me start by explaining how network side channel leaks works at a high level. An adversary observes the traffic shape of a victim application, which includes the packet sizes and timing, and from that it aims to infer the secret of application. So consider an application running inside a virtual machine in the cloud, sending requests to an external client, an adversary with physical access to a network element in the path of the application can directly observe the traffic shape of the application. Alternatively, an adversary can rent a cheap unprivileged virtual machine, co-locate itself with the application virtual machine in the cloud, and then generate cross traffic that would induce contention with the application's traffic at a shared network link, which could be the NIC of the physical server or even a top of the rack switch, and based on the variations observed in its own traffic due to contention from the application traffic, an adversary can indirectly infer the shape of the application's traffic. The plot on the right here shows an actual attack where an adversary could identify the unique size of the different files from a corpus as these were submitted, and the adversary could observe this and infer this simply based on the sizes and timing spikes observed in its own ping traffic latencies. And private has shown that one can learn a lot of sensitive information just from the observations of the traffic shape. For example, one can identify the web page requested, which video is streaming content of voice over IP conversations, and even uses medical and financial secrets from health or financial services hosted as a software as a service application in public cloud. So you can see network side channels can reveal a lot of sensitive information, and this should be of concern for cloud providers. And we present a system called Pacer to mitigate these kinds of leaks for cloud tenants. At its core, Pacer shapes and application traffic to make the shape independent of secrets, and we present an abstraction of clock panel to enforce secret independent traffic shapes by design for an application to mitigate the leaks. For infrastructure as a service cloud tenant, we provide the design and implementation of a virtualized clock tunnel instance, and one of the key challenges is building such a tunnel is to ensure that the tunnel itself is secure from the other micro architectural side channels on the platform. And for this we develop a novel masking plus batching based mechanism, which I will describe in the talk of the paper. We also discuss other ideas related to traffic shaping strategies and exploiting public inputs to allow for shaping bursary traffic of an application efficiently. While still protecting secrets, we also provide a gray box profiler that can automatically compute network shades for an application while requiring minimal effort inputs from the application itself. You can also find detailed evaluation results and a formal proof of security of our system in the paper. Here I will describe the detailed clock tunnel extraction, and it's designed for enforcing traffic shaping. So the key abstraction of POG tunnel is essential, what encapsulates and shapes the network traffic between any pair of communicating nodes and can be used to shape the traffic of an arbitrary guest VM. The key property that the tunnel provides is that the shape of the traffic inside the tunnel is secret independent, so that an adversary can not learn anything even from the observation of the traffic inside the tunnel. To achieve this high level property, the tunnel endpoint needs to satisfy two high level requirements. First, it needs to make the payload traffic unobservable, and for this it must ensure that all packet sizes are secret independent. For example, they all have the same fixed size. An application packet generation rate may vary based on flow control, which may be itself dependent on secrets. So the tunnel must hide the flow control information by transmitting dummy packets if there is no payload from the application. Now, to hide the padding and payload packets, all the packets must be encrypted after the padding, and the padding information must be injected in the packet headers in such a way that it would be delivered at the other endpoint, and that the other endpoint would generate similar responses for all the packets, because otherwise an adversary could see the differences in the traffic in the other direction and distinguish between padding and payload. And the second high level requirement is that tunnel must ensure that all packets are transmitted at secret independent times, so preferably on a schedule that is predictable and public, and there should be no deviations from the schedule in a way that could be correlated with application secrets to protect the traffic of an application running in a cloud virtual machine, where there will be one endpoint of the tunnel to be integrated with the virtual machine hosting server covering the shared NIC of the server, and the other endpoint should be implemented somewhere on the client's premises, such as a middle box or even on the client device. Here we describe the design of the tunnel endpoint for the application to the endpoint can of course be implemented symmetrically. So conceptually, the tunnel endpoint can be implemented by adding shaping layer right at the top of traditional network stack. In the guest kernel, the application receives requests from the network, and it generates response and shares it with the shaping layer. The shaping layers installs the transmit schedule based on the traffic shape computed for the application, and then at each time defined in the transmit schedule, it generates a fixed size packet using the payload bytes from the application's response and adding padding wherever necessary. And then this prepared packet will go through the lower layers of the network star. It could be encrypted using a traditional IPsec layer, and then it would be transmitted into the tunnel. How now, unfortunately, the simple conceptual design is still vulnerable to timing leaks that could arise due to microarchitecture side channels on the platform. Note that the packet transmission time is chosen at the shaping layer right at the top of the network. Information which is again shared from the modified guest TCP layer, and essentially it pauses transmission on the schedule when there is congestion on the network, and it resumes transmission when the congestion is resolved. Note that reacting to congestion control signals is only required to ensure network stability and performance. It does not have any security implications because congestion is a publicly observable event on the network. You can find more details about our design and implementation in the paper. And now I will briefly talk about our evaluation. So we evaluated the security and performance overheads of our solution. For security, we evaluated the accuracy and precision of a state-of-the-art CNN based attack classifier on the shape traffic, and we also built a formal model of high pace to gain confidence in its design and implementation for performance. We analyzed the bandwidth overheads incurred due to places padding of static purposes for different services, and the trade-off between the bandwidth overheads and privacy guarantees that we can achieve after using public input based worker partitioning for traffic shipping. We also measure the overheads on the client latency and peak server throughput sustained by a medical website that serves static medical web pages, and we evaluated the client experience when streaming videos from a video service which is set up as both a single tier application as well as a two-tier application. So we observed that Pacer incurs moderate overheads and bandwidth latency, and the throughput still in the order of hundreds of milliseconds, which could be further reduced by optimizing the transfer schedules that we compute for traffic shaping. Nonetheless, the impact on the end client's experience is actually minimal For example, we observe that video client experiences no jitter when streaming videos despite traffic shaping. The exact overheads depends on applications. Upcoming traffic shapes, and Pacer provides us the way for developers to configure the trade-offs between the overheads that is willing to incur and privacy guarantees that it wants for its applications. To summarize, Pacer is a traffic shaping based solution to mitigation network side channels leak for infrastructure as a service cloud tenant. It provides a secure by design solution in that both its traffic shaping strategy as well as enforcement of traffic shaping is secure. It is also efficient as it allows exploit public inputs to reduce the overhead sub traffic shaping for an application. It also reacts congestion control signals that provide a practically unusable solution. And finally, Pacer requires minimal changes in the guest application to leverage the traffic shaping solution, and a modest amount of changes in the cloud hypervisor and the guest OS to support the solution. We have open source all of our code, and you could check it out if you are interested in that. So now I will thank you, and I am very happy for your questions. I will take them. If you have any question, you can comment on my video and I will answer your questions